One of the key...
All right, so the key figure that we will discuss is going to replace Einstein. Again, this is news for you guys. The biggest name in physics during the 20th century was not Einstein. This guy, his name is Bohr.
Figures in the quantum revolution.
And unfortunately, Bohr is no Einstein.
Is a young Dane with a tendency to mumble. He's the scientist on the right. His name is Niels Bohr. And from childhood, it's physics that consumes him. Once, while playing goalie in an important soccer game, he starts scribbling equations on a goalpost. Only the screams of an ardent fan snap him out of his reverie in time to stop an opposing player's potential goal. At school, he's an excellent student, though he seems to have a serious phobia about writing. As a graduate student, he dictates his entire doctoral dissertation to his mother, causing a family fight when his father insists that the budding PhD learn to write for himself. He never does. After his marriage, his wife gets the job. In 1912, shortly after receiving his doctorate, Bohr travels to England. He comes to Ernest Rutherford's laboratory just 1 year after Rutherford makes a startling discovery about atoms.
All right, so he goes to England in 1911, according to this, and then starts working on the problem of the hydrogen atom. He spends about 2 years trying to solve that problem. And then he solves it. And then in 1923, I think he wins the Nobel Prize, or 1920.
When Niels Bohr arrives in Manchester, Rutherford is ready to abandon his model of the atom, but Bohr sees a way to save it.
He was so excited, he canceled his honeymoon. He had to delay his wedding, cancel the honeymoon, and his poor fiancée, instead of going on a luxurious honeymoon, had to take dictation, as her husband dictated one of the greatest masterpieces in physics because he himself could not get himself to write down the paper.
What he proposed was...
All right, guys.
You would not allow the electrons to move in any orbit about the nucleus, as you could according to classical theory.
All right, so what happened? Bohr gets an idea about the hydrogen atom problem that he's working on. He thinks that he can solve the problem. So what does he do? Postpones the wedding, cancels the honeymoon, and he says, "Honey, now that you're available, why don't you write up the paper for me?" That's it. So the question is, can you do that sort of stuff today and get away with it? It's like a divorce attorney's dream, as you can't get away with that sort of stuff. All right, so that's the difference between a guy who wins the Nobel Prize and a guy who works at a community college. It's the wife. All right, I mean, she just put up with that kind of nonsense. So what exactly did he come up with, which was so worthy of postponing the wedding and canceling the honeymoon? He must have come up with something amazing,
But
in order to solve this problem.
Only to occupy certain very well-defined orbits about the nucleus. There would be an orbit here, an orbit here, an orbit here, but there would not exist orbits between these.
There's nothing in between. In between exists nothing. And that's very non-Newtonian. If you take the Earth and you could move the Earth a little bit closer to the Sun, no problem. Would have a different orbit, would be stable, would have a different time to go around the Sun, no problem. That you cannot do with an electron around a nucleus. You cannot just change the orbit by a little bit. You have to change it by, so to speak, a lot.
All right, so he was able to solve this problem by introducing a bunch of postulates. Remember postulates? Einstein's favorite way of solving problems. What's the postulate again? Guys, postulate is an assumption. Comes up with some assumptions. And he says, I'm going to come up with a theory based upon these assumptions. His number one assumption is electrons can only move within these certain orbitals without radiating energy. All right, so there are orbitals within which the electrons can move without the radiating energy. That's it. Because normally, if the electron is moving about the nucleus, it would radiate energy. It will lose all of its energy and collapse into the nucleus. He says, oh, let's stop that from happening. Let's assume that there are orbitals around the nucleus within which the electrons can move without radiating any energy. And then the next, so you got these orbitals. The electrons will just stay on these orbitals. They cannot be in between. They will only be on these orbitals, and they can move on these orbitals without radiating energy. The next one is electrons can move between the orbitals by jumping between the orbitals. All right, so they will absorb energy, quantized energy, and then jump up to the next one. So the quantum of energy is going to be absorbed, and they will stay there for a fraction of a second. And upon jumping down, they will release that energy. So there's an absorption of energy, and there's a re-emission of energy. So the energy gets re-emitted. So the energy gets absorbed, quantum jump. The electron stays there for a fraction of a second, and then upon releasing the energy or re-emitting the energy, it does a quantum jump inward. All right, these are known as quantum jumps. So we got, actually, there are three postulates. We will just focus on two of them because advanced physics course. All right. So Quick review. What did J.J. Thomson discover? Electron. What's the nature of electron? It's a particle. It's got a known charge and a measurable mass. Definition of ionization energy is the amount of energy required to knock an electron out of the atom. What defines the size of an atom? The radius. Experimental facts regarding the size and the ionization energy of the hydrogen atom. Size is half an angstrom. Ionization energy is 13.58 electron volts. So what is the Rutherford planetary model of the atom? Nucleus, the positive charge at the center, negative charge, or charge is moving about the center. Exactly the same way the planets move about the sun. Why did he place the electron half an angstrom away from the nucleus? Because that's what the experiment suggested. The scattering experiment suggested that the atom had a size. The size of an atom was half an angstrom. So which means that you have to separate the negative charge from the positive charge by that distance. If most of the atom is empty space, why then the masses don't go through each other? They don't go through each other because of electrostatic repulsion. Like charges repel each other. What was wrong with the Rutherford planetary model? Electrons orbiting the nucleus would radiate up all of their energy within a fraction of a second and then collapse into the nucleus. Because orbital motion is accelerating motion. Accelerating charges radiate energy, which means that they would lose energy within a fraction of a second. Within 100th millionth of a second, the atom would collapse. So the orbital motion is an accelerating motion. And the accelerating charges lose energy within a fraction of a second. What's the Bohr's first postulate? The first postulate is there are orbitals around the nucleus within which the electrons can move without losing energy or radiating energy. The third postulate for you guys is the second postulate. Electrons can jump between the orbitals by absorbing and releasing energy. So they can jump between the orbitals by absorbing and releasing energy. All right, so let's get back again. The first postulate, you got these orbitals within which the electrons can move without radiating energy. All right, electrons cannot exist in between the orbitals. They can move within these orbitals without losing energy. And they can jump between the orbitals by receiving and releasing energy, by absorbing and re-emitting energy. Absorption, re-emission. Publishes his results in 1913. And then wins the Nobel Prize in, I think, 1922.
And that's when the problems became obvious. Being radical, Bohr had gone further, far enough to propose that an electron could exist only in certain orbits, which was contrary to Newton's laws. Then, contrary to Maxwell, Bohr said the electron would radiate or absorb energy only when it jumped between these definite orbits. Those proposals were more than merely contrary. In fact, in the world of physics, they were totally against the law.
All right, let's
Then,
get back.
could exist only in far enough could exist only in certain orbits,
I want you to notice something.
which was contrary
The electron is going to jump. It's going to make a
to
transition
Newton's law.
from one state to another. That's known as a quantum change. Its electron is about to
Then,
jump.
contrary to Maxwell,
Notice that it released energy. Look at the color. It's red.
Bohr said the
So it's a definite frequency got re-emitted or released
electron would radiate or
or radiated.
absorb energy only
Now, notice that now it's violet. So every time the electron makes an inward jump, the energy is going to be released. At first it's red, now it's violet.
when it jumped between these definite orbits.
Quantized energy is being released or absorbed, which means that the definite frequencies are being released or absorbed. Within the color spectrum, you will see colors every time there's a transition.
Those proposals
All right. All right, so he publishes his results in 1913, and immediately
Bohr's idea
there's a reaction.
that electrons can have only certain orbits draws inspiration from other new theories that suggest heat and light come in units that can't be divided, called quanta. But applying this quantum idea to matter is practically sacrilegious. In fact, most physicists disapprove of Bohr's theory. Whenever they meet, they scoff at the idea that an electron can be in some places but not others, that matter comes in some sizes but not others.
If it's not nonsense, at least it doesn't make sense.
This is just a cheap excuse for not knowing what's going on.
The assumptions are too bold, too fantastic. They can't be right.
In time, two camps emerge. A group around Bohr, which believes in his so-called quantum theory of matter, and those who cling to the classical view. No less than the true picture of nature is at stake.
All right, guys, what's the difference between those who believe in him and those who oppose him?
But not others. Bohr's theory.
These are the guys who are opposing him. They're not impressed. They're not impressed at all.
Whenever they meet, they scoff at the idea that an electron can be in some places but not others, that matter comes in some sizes but not others. And those who cling
And versus these
to
people.
the classical view. No less than the true picture of nature.
So what's the difference between the people who oppose him and the people who believe him? What do you guys think? All right, guys, this is a bit of a visual question. What's the difference between the people who oppose him and the people who believe him? All right, let me tell you what the difference
Is
is.
at stake.
People who oppose him,
The idea that an electron can be in some places but not others. That matter comes in some sizes but not others.
versus the
Real
people
matter.
who believe him. People who oppose him are bearded, and the people who believe him are well shaven. All right, so that's the difference. Got it? You weirdos, what do you think the difference is? The older generation don't buy his ideas at all, right? The younger generation, this is the Disney world. I mean, you guys are part of the Disney world right now because you don't have a lot of life experiences. This guy comes up with some bullshit, and then he's trying to make it stick. These guys don't know any better. These guys are in their 20s or their 30s or whatever. They're not as well versed in physics, and they're going, oh, this guy has some ideas. He solved the hydrogen atom problem. Really? Did he really solve the problem? So here's the question. Where do these orbitals come from, by the way? That the electrons move about without losing any energy. All right? How do electrons know where these orbitals are so that they could get up to speed? How do they get up to speed? How do they slow down if they're moving at that speed? Every single hydrogen atom in the universe is identical to every other hydrogen atom, which means that in every single hydrogen atom, you should have these orbitals, and only the electrons magically know where these orbitals are. They will just get up to speed and merge into that orbital and stay in that orbital. How do these orbitals come into existence? Why is it that the electrons are not radiating any energy while they're accelerating? It's bullshit after bullshit after bullshit. All right, the older generation is looking at it and says, what the hell is wrong with you people? This is not physics, this is something you made up. And the only person who's completely unaware of how stupid the idea is the wife. Agreeing to actually postpone the wedding, cancel the honeymoon. 2 years of this nonsense? Are you kidding? Are you kidding? Older generation was not impressed at all. So, was Bohr able to explain how these energy orbitals come into existence? No, he said, let's assume that they do. That's called an assumption. He didn't justify it. There was no way of justifying something like that. That's the reason why it's called a postulate. He said, I don't know how they come into existence, or else we would not have these atoms. Got it? He was trying to come up with a stable atom. He said, let's assume. Don't say assume, because as soon as you say assume, somebody say, let's not assume. He says postulate number one. There are these orbitals within which the electrons can move without radiating energy. Postulate number two, electrons can jump between these orbitals, absorbing and emitting energy. That's it. These are postulate assumptions, assumption after assumption. He's not justifying it. He's trying to create a stable atom. So was Bohr able to explain why the electrons were able to orbit the nucleus without radiating energy? He said, no, absolutely not. He said, let's assume that they're orbitals within which the electrons can move without losing energy. That's it. Let's call it the postulate number one. All right? He did not justify anything. He just came up with these postulates. He said, these are the postulates that should give us a stable atom. He had the mathematics to back it up. R is going to represent the location of these orbitals. Here's the first orbital. Here's the second orbital. Here's the third orbital. Shit for you guys to focus on. Guys, I want you to take a look at all the symbols. N represents number one, number two, number three. You guys remember N from the Balmer's series. That magic shit starts to appear. H is your Planck's constant. It's a constant. Pi is a constant. K is the strength of the electrostatic force. M is the mass of an electron, a point particle that you cannot see, but whose mass you can measure. E is the charge of an electron. These are known as the constants of nature. Everything that you're looking at are constants of nature. And that's going to play an important role in terms of the creation of the universe. Magically, when you put the numbers in, what's the size of the hydrogen atom? Experimental size of the hydrogen atom is 0.52, or it's going to be 0.53 times 10 to the minus 10 meters. Okay, I gave you a little bit more exact number. The number that I gave you was 0.529, which is the same as 0.53 times 10 to the minus 10 meters. Okay, theoretical number is this. The experimental number is the same. So what does it tell you about the theory? Theory is good. The experimental and theoretical numbers match.